Okay, good day. This is Math 130, Introduction to Statistics. I'm Professor McCulley. This is Lesson 10, Conditional Probability and the Multiplication Rule. Let's get to it. Today, we're going to find the probability of a given event, given that one or another event has already occurred. We're going to distinguish between independent and dependent events. We're going to use the multiplication rule to find the probability of two or more events occurring in sequence and to find conditional probabilities. So first, let's define conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of event B occurring given that event A has occurred is given or denoted by P. B with the horizontal bar there, or not horizontal, vertical bar there, A, and we read that probability of B given A. So an elementary example. Two cards are selected in sequence from a standard deck of 52 playing cards. What is the probability that the second card is an ace given that the first card is a king? Well, if the first card is a king, we have one less card. If the first card then we have only 51 cards left. All right, but there's still four aces. Still, come on, learn to spell S-T-I-L-L. There are four aces. So the probability, and this is classical probability, of P of B given A, and in this case, probability of an ace given king will be 4 out of 51, and we can leave it like that, or you can put it in a calculator, that's fine, but we want to move on. Another example using a table. The table below shows the results of a study in which researchers examined a child's vision and the presence of a genetic marker in the child. Find the probability that the child was nearsighted based on the presence of the genetic marker. So in this time, we have the probability that the kid that was chosen is nearsighted given that they had the genetic marker. And since we say it's given that they have the genetic marker, we can essentially get rid of this whole column and only concern ourselves with this particular column. We are saying that he has, or that child, girl or boy, has the genetic marker already. And we want to know the probability that they were not nearsighted if they are already in this column. So in that particular instance, we have 157 over 204. And I don't think that reduces. So let's see here. We'll quit. Let's go ESC. Quit. Yes, I want to quit to main menu. Let's quit. Yes. There we go. Now I forgot the numbers. 157 over 204. 157 divided by 204. That's too many fours. Hit enter. So 0.770, because I'm going to go 3 decimal places and I'll round that one up. 0.770. 0.770. So 77%. That's possibly significant, I suppose. But that's how we're going to calculate that. So moving on. Definition. Two events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. Two events, A and B, are independent when the probability of B given A is equal to the probability of B, or if the probability of A given B is the probability of just A. Note that two events that are not independent are dependent. So let's talk about an example. Classify the following events as dependent or independent. Rolling a 4 on a 6-sided die, then getting a heads on a regular coin toss. Well, since the roll on the 6-sided die does not affect the coin toss, we're going to call these independent events. All right, drawing an ace from a standard deck of cards, then without putting the ace back, drawing a king from the deck. We've already shown that this is a dependent event because if you draw the ace from the standard deck, you have now changed the probabilities. Instead of having one out or choosing a single card out of 52, we are drawing a single card from a deck of 51. So those are dependent. This one's a little bit harder. Being a fireman A, then getting a second-degree burn B. So what do you think? Is it dependent? Getting a second-degree burn, is that going to change based on the fact that you're a fireman? I think that if you are a fireman, you are certainly going to put yourself into situations where you are more likely to get that second degree burn. So I am going to say that those are dependent events. Let's move on. Multiplication rule for probability of A and B. The probability that two events, A and B, will occur in sequence. Probability of A and B would be the probability of A times the probability of B given A. If A and B are independent, then it's just the probability of A times the probability of B. And this can be extended to any number of sequential events. So let's do an example. Two cards are drawn from the standard deck without replacing. The first card, what is the probability of drawing a 2 and a king? And so these are definitely dependent events because we are without replacement. So we are changing the deck. And so the probability of drawing, let's see here, a 2 and a king would be the probability of drawing a 2 times the probability of oops, I did that back. So probability of a king and then a probability of a 2 given king. Probability of a king and then times the probability of a 2 given that we have a king. That's what I want. So the probability of giving a king is going to be 4 out of 52. And since I have a king, I have one less card, so I only have 51. But there are 4 2s in there, so I have 4. And I'm just going, since my numbers aren't going to come out real nice, I'm just going to let the calculator do that. 4 divided by 52 times 4 divided by 51, and we get 0.006, so 603, two zeros. 0.00603. Not the best chances in the world. Two cards are drawn from a deck. The first card is replaced, and then the deck is shuffled before the second drawing. What is the probability of a 2 and a king? Well, these two are definitely independent events, and a king, because in each case we still have 52 cards. So this will be 4 out of 52 times 4 out of 52. And so let's go to the graphing calculator, and just to review some of those calculator things, I'm going to go second and I'm going to go entry and bring up what I had and just change that last one to a 52 so I don't have to change it. And this one's 0.00592, 0.00592. Slightly worse chance now that you've put the king back in. Okay, Carpal tunnel surgery is 92% effective. What is the probability that 3 carpal tunnel surgeries done at a single hospital are effective? Well, in general, I would say that one carpal tunnel surgery does not in any way affect the next one, and so that they are independent events. So if I'm going A, the probability of 3 surgeries or 3 effective surgeries will be the probability of each of them. So 92 or 0.92 times 0.92 times 0.9, come on, 0.92. Let's do a better job. Apologize, I should do better. 0.92 equal to 0.92 to the third. We'll just do that. 0.92 raised to the third is, so we have a 77.9, 0.779 chance that they will all be effective, or 77.9%. What is the probability that none of the 3 surgeries are successful? All right, probability that 3 unsuccessful. Well, if the probability that they're effective is 92%, the probability that they are not effective would be 8%. So 0.08 times 0.08 times 0.08, which would be 0.08 to the third. 0.08, not 5, 8 raised to the third gives me, I got 3 decimal places and then a 512. So 0.123512. So that's a very small chance that none of them will be successful. And then C, what is the probability that's at least 1? Well, if it's not 3 unsuccessful, that is all of the remaining. It could be 1 successful, 2 successful, or all 3 successful. So the probability of at least 1 is going to be the complement of probability 3 unsuccessful, which in this case would be 1 minus 0.00512, which we can, again, graph and calculator learning time, 1 minus second, hit that minus button to get the answer, 0.999. Well, we're going to go out past since that's, these may be significant later on. So 0.995 is what we'll say. 0.9995. So a pretty good chance that they'll get at least 1 right. All right, that's all I got for this particular one. So today's Marvel fun fact of the day, the opening of The Incredible Hulk, the movie in 2008, is an homage to the 1977 TV series of the same name, starring Bill Bixby as David Banner. 2 things about this. This show came out when I was 6 years old, and I loved every second of it and never missed an episode. And I also know that they changed the name to David Banner because back in the 70s, they thought that Bruce was too effeminate of a name for Americans' tender ears. Glad that we have grown a little bit from that. So that's all I got for today, folks. Have a good one. Bye.